Okay, so in this video we are going to discuss the concept of conditional probability. So, recall from previous videos the concept of a probability space. So you have a sample space, which I'll draw as a box, which is this set containing all outcomes for a possible experiment. You also have a collection of subsets of the sample space, which we call the set of events, given this curly F. And we have a function p which attaches to every single event in f a value between 0 and 1, and this structure is called a probability space if it obeys a bunch of axioms. So the axioms it has to obey are the set of events has to obey the axioms that firstly the empty set and the whole space are events. So nothing happening and any outcome happening are events. 2, if E is an event, then E complement, the event that E does not happen, is also an event. And 3, that if En are all events, then the countable union of those events, providing they are all disjoint, is also an event. In fact, it doesn't matter if they are disjoint or not. No, it doesn't matter if they're. They don't need to be disjoint at all. Sorry, it's just any old union. N is equal to 1 to infinity En. That's a mistake. It doesn't have to be disjoint whatsoever. Those are the axioms it has to obey, and those are the axioms of what is known as a sigma algebra of subsets. So if it obeys these axioms, it's a collection of subsets. Remember that this F is a subset of the power set of your sample space, and if it obeys those axioms, it's called a sigma algebra of subsets. So F needs to be a sigma algebra, and the probability function P, which maps this sigma algebra of events onto, why do I keep putting the dots there, onto 0, 1, has to obey a bunch of axioms too. Firstly, the probability of the whole space needs to equal 1, and conversely, the probability of the empty set needs to equal 0, and 2, the probability of a disjoint union, n is equal to 1 to infinity of En. Firstly, we know that that is also an event from this property over here, so we can take its probability. This is equal to the sum from n is equal to 1 to infinity, so the limit of the partial sums of the probabilities of En. So those are the axioms it has to obey to be a probability space. Now the concept of conditional probability is basically reducing down the idea of a sample space. So it's very similar to the concept, for instance, of if you have seen group theory, you've seen groups and subgroups. What we are basically saying is, can we find probability spaces within our probability space? So for instance, if we take an event E, that's a subset of the sample space. What if we say E is our new sample space, So we say ignore everything in E complement, and we're going to just consider E as a sample space now. And then we can say we need now, to make it into a probability space, we need a set of events, and we also need a probability function which will attach a probability to each of the events. So how do we make a set of events? Well, basically, we say if A is in F, then we'll define a new set of events for E, which we might call F bar. We'll define F bar to be all of the elements of F intersection E. So basically, if you have another event, let's say A here, then we're going to potentially define, let's say, shall we call it A bar, which is just going to be the intersection of it with E. So the bit of the event A, which is in E, which is the natural thing to do. We want to create a new set of events that is relevant just to E. We're now considering E as our whole space. So we just take any event in our bigger space and restrict our attention to the bit that's in E. Now we want to prove that that obeys the axioms of this sigma algebra up here, otherwise it's not going to be a probability space, is it? So, first axiom then, just draw some lines across. The first axiom then, the empty set is an element of F bar we want to show. How do we know that? Well, the empty set is an element of F. The empty set intersection E, so empty set is an element of F, and the empty set, often F bar would be denoted F intersection E, is the way you denote this new set of events over here. So if this is an element of F, then phi intersection E is still equal to phi, so phi is therefore an element of F bar, but I'm now going to write that F intersection E as this new set of events. The set of events restricted to E would be the way it was read. Now we want to prove that the whole space is an element of F intersection E. But what is the whole space now? The whole space isn't the omega anymore, it's E. So we want to prove that E, rather, this isn't property 2, this is just the second part of property 1. We want to prove that E is an element of F intersection E. Well, that's easy, because the whole space is an element of F, and the whole space intersection E is equal to E. So that implies that E is an element of F intersection E. So that's very easy. So we've proved that it satisfies axiom 1 of a sigma algebra. We now want to prove that if E is an element, well, we don't want to use E. We want to prove that if A is an element of F intersection E, then we want to show that A complement, and remember what A complement now means. A complement means E minus A, because E is our entire sample space. So basically, if I take a little set here, and this is A, I should have used a different letter because I've already used A here, but if I take an event A, which is in my new sample space that I'm considering, which is just E, and I want to take its complement, then it's all the things that are in E and not in A now. Okay, because we're considering E as our new sample space. So we want to prove that A complement is an element of E subtract A. Well, basically, what we can say is, because of the axioms of this up here, basically what happens is, for instance, if I say if A is an element of F intersection E, then it implies that there exists an A bar, we'll say, where A bar was an element of F. So there was a bigger A, if you like, a bigger A, just like in here. This is the new A here, and this is the bigger A, which we're now going to swap the notation. I'm going to call A bar the original thing, and A the new thing, which is really confusing because I called A bar the new thing and A the original thing. But we'll call A bar the original thing in the bigger algebra, the bigger thing in the larger sigma algebra, which we are intersecting with E to get this new thing. So there existed something that was bigger in F, which we intersected with E to get this element A. Now it might have been the same size, because A might have been an element. For instance, if A was this, then you can imagine that A might have just been an element in F that was just completely contained within E. So when we intersected it with E, we just got the whole thing back again. So it doesn't necessarily have to have it, but there is a corresponding element in the sigma algebra F, such that when you intersect that corresponding element with E, you get your A. Okay, and call that element A bar. Then A bar complement is an element of F. So basically, if this is A bar, then the complement of that, all the things that aren't in A bar, is an element of F. And basically, when we intersect that, when we intersect A bar complement with E, then that is equal to, we'll get all the things that aren't in A that are in E, and it will be basically the complement of A in E. So it's equal to E minus A, basically, i.e. it's equal to A complement, where we're considering it as a complement in our new probability space, in our new sample space, rather. Okay, so it does obey that property, and now the third property is that it has to be closed under countable unions, and again that's follows really straightforwardly. So if we take 3, so if we have some ENs which are elements of F intersection E, so they're elements of the sigma algebra restricted to E, that implies that there existed En bar such that when you intersect En bar with E, you get that's equal to En. So there existed some elements that were in the bigger probability space that when you intersected them with the smaller, when you intersected them with our new sample space, gave you that element. And basically, we can union together these larger elements because they were in the sigma algebra. They were ENs, which were in this original sigma algebra. So union of E bar n is equal to 1 to infinity, is an element of F, and then basically we just restrict it to E. So we just say E intersection this union, n is equal to 1 to infinity E n bar, will be an element of F intersection E. And then we just apply the fact that intersection distributes over union, so we can say that this is the union of n is equal to 1 to infinity En intersection E, and that should be En bar, and En bar intersection E is just En, so we can say that this is equal to the union n is equal to 1 to infinity En, and that implies that it's an element of F intersection E. So there you go, that proves that it's closed under countable unions. So it's obeyed all of those properties, so that's all good. Okay, so the final thing we want to check is we want to rewrite the theory of our probability measure. We want a probability measure on this new, basically what we've done, just to recap, is we've taken our initial sample space here with this original set and an original probability measure. We've taken took an event inside it. We're saying this is now our sample space. We've now made a new set of events, which is F intersection E. What we now need to do is write a new probability measure on there, which I will call, I'm going to call it P bar, which is again really confusing. So P bar is going to be our new probability measure, and probability on this new new sample space is basically conditional probability. Conditional probability. It's saying, given the fact that the outcome is in this event, so it is in this smaller set here, what's the probability of each new event in here now? It is in here now, so ignore everything out. What's the probability now? That's conditional probability, saying, given something else has happened, given we were in event E, given E has happened, what is the probability of these other events happening? And these new events are going to be in this new sigma algebra we have devised. So how do we modify probability? Well, the way that you do it is you write the probability of, so A given E is equal to, well, right, okay. So firstly, this is confusing. What this means, this notation means what is the probability of event A happening given that event E has happened. So that in a way means the probability P bar of A intersection E. So basically A is another event in this larger sample space. The confusing thing about it is that A is not the restriction of this to E. It's not A intersection E. So in our lingo of making a smaller probability space, what you'd say is you'd say, here's event A, we're now just interested in the bit that intersected with E, and then we're taking P bar, this new probability measure of A intersection E. But it's not written like that. It said the probability of A given E. So what it means is exactly that. It's saying, given E has happened, what is the probability of this bit of A that intersected with E? The bit of A that can still happen, basically. And it's written probability of A of given E. And it's basically equal to P of A intersection E. So that's the old probability measure. So the old probability measure of just this intersection bit. And then you divide it by P of E. And we want to prove that that is a probability measure, that that is a valid probability measure. It's certainly intuitive that that's what you do. Basically, you're saying, take the probability of these intersections here, and then scale it to the fact that probability of E is now the whole sample space. So firstly, let's check that probability of the whole firstly that the probability of the empty set is still equal to 0. Well, actually we will write it out properly. P bar of phi, which is equal to the probability of phi given E, is equal to the probability by definition. It's the probability of phi intersection E over the probability of E. Right, so the probability of E is some constant, but probability of phi intersection E, the empty set intersection E is still the empty set, and the probability of the empty set is equal to 0. So this is therefore equal to 0 because this numerator is 0. So that's that axiom done. Now the probability of the whole space, but the probability of the whole space is now E. So the probability P bar of E is going to be the probability of E given E, which is equal to the probability of E intersection E divided by the probability of E. Now the probability of E intersection E is just the probability of E, so that's equal to the probability of E divided by the probability of E, so that's equal to 1. Excellent. That's that first axiom done completely now. So now what we want to turn our attention to, and I'm just going to get a new piece of paper, is the second axiom of a probability measure. So we now want to prove that under countable unions, P bar of okay, so second axiom, that if you have E, well, let's say A, which is equal to the union of n is equal to 1 to infinity, disjoint union, n is equal to 1 to infinity of an. Now I'm going to explain exactly what I mean, because there's a big danger we're going to get confused here. There's a big danger I'm going to get confused here. This is the most difficult one to prove. So okay, and we need to be very careful about what I'm defining here. So here is our E, and I'm going to say A is some event in this new probability space I've got. So E with F intersection E and P bar as our new probability space, and this is our, we haven't shown that it's a probability space, we're in that process at the moment, sigma F, and this is our larger probability space over here, P. And I'm saying A is some event in there made up of little events here, A1, A2, A3. Now, I want to take P bar of A, which is, what is that? Yes, okay. I want to take P bar of A. Now, the first thing I've got to do is I want to write this as probability of something given E. Now, the probability that you can't see this. The probability that I stick in here is the bit that was in E. The bit that I stick in here has to be the larger thing that was in our original probability space. So basically I say, if A was if A is an element of F intersection E, then there exists an A bar, which is an element of F, such that, you know, A bar intersect E is equal to A. And similarly with AN, all of the ANs are an element of F intersection E. There exists... I should have done those ANs actually first, so let me just put the ANs. So I was doing that for the little bits first, and then we'll just define big A bar to be equal to the union n is equal to 1 to infinity of little a bar n. Now there's a slight difficulty here, which is that how do you know that these little a bar n's are disjoint? I'm struggling with that myself. How do you know? If there are elements of that, how do you know that they are disjoint? I knew this bit was going to get me the most. Disjoint. We need them all to be disjoint, but how can you get that? Are the little ANs part of the original sigma algebra? Yes, okay, that's what I'm going to show. Okay, it'll be easier, basically. Or with it. Maybe it would be easier to do it that way. No, we need to show this. Okay, the first thing I'm going to do is... Yes, that'll be what I do. Right, okay. So, let's go back to these axioms of the sigma algebra over here. Specifically, this axiom here, and this axiom here. Now, the axioms of the sigma algebra, so we're considering the bigger sigma algebra here for a second. The axioms of the sigma algebra say that A1 union A2 is an element of the sigma algebra if A1 and A2 are elements of the sigma algebra, okay? Now, the second axiom of a sigma algebra said that the complement is also an element of the sigma algebra. So if that's an element of the sigma algebra, it implies that the complement is also an element of the sigma algebra. Now apply basic axioms of set theory. This says what is in A1 and is in A2. So then we're asking what is not in either of them, which is the same thing as what's not in A1 and what's not in A2. So the intersection of A1 complement and A2 complement is an element of F. And since A1 and A2 were arbitrary, we might as well just write this A intersect, well, let's do B1 intersect B2, where B1 and B2 were just arbitrary elements of the sigma algebra. Because of course, if A1 was an element of the sigma algebra and A2 was an element of the sigma algebra, it implies that A1 complement and A2 complement are elements of the sigma algebra, but they're just arbitrary elements of the sigma algebra. So indeed, we arrive at the axiom that if B1 and B2 are elements of the sigma algebra, then B1 intersect B2 is an element of the sigma algebra, and that's just derivable from the axioms that we stated of sigma algebras. Okay, so here goes. If these little ANs are elements of the sigma algebra, then it follows that the are elements of this restricted sigma algebra, then it follows that there does exist a larger set outside of E such that it was in the sigma algebra. Then we can say by this property down here that AN intersect E, AN bar intersect E, this bigger thing that was intersecting with E to give E is also an element of the original sigma algebra. Therefore, it follows that all the little ANs, all these original ANs that we started off with in the restricted algebra, so all of these that we were coming up with here, they are all actually elements of the sigma algebra. So basically, what I'm saying is that any element that is in F intersection E is also in F. So this restricted sigma algebra on our new probability space is in fact a subset of our original one. So that's going to be very useful because it means that we don't have to continuously jump onto these larger ones. So basically, I was now trying to do the probability of this A. So I'm going to remind myself where I was. A is equal to this disjoint union, n is equal to 1 to infinity, ANs. And A and all the ANs are elements of the sigma algebra intersection E, which is a subset of the sigma algebra. So that it implies they're all elements of this. Now, I wanted to take P bar of A, which is equal to what? Well, it's equal to the probability of A intersect E, because I would have had to originally say, you know, something along the lines of where am I? Here, along this conditional no, sorry. It's the probability of A given E. So basically, how am I going to explain this? Right. Okay, I'm going to draw a picture. That'll help. So we've got this sigma algebra, this bigger, sorry, not this sigma algebra, this sample space here. We've got this event E. I have got some A here, which is made up of all these little pieces that I'm unioning together, this disjoint. I am saying now that A and all of ANs are elements of the original set of events. So I can basically take P of all of these and get an answer. That is very, very useful because now what I can view A as, instead of saying I need a bigger set which intersected with E to give A, I can just say, well, just consider the set A. The set A is in this larger sigma algebra, and it intersects to give A, it intersects with E to give A. So I'm just considering A as my bigger thing. So this P bar of A is equal to the probability of A given E, isn't it? So that's what I'm doing. It may seem a bit trivial, but to prove that, I can't think of a better way to do it. So basically, I'm just saying, let the element of the set of events in the bigger probability space, which is going to intersect with E to give the event A in this smaller set of events for this smaller probability space be the set A itself. So don't make it bigger, basically, because otherwise you're going to get this issue of how do we know that when we extend the little ANs out again, we're going to get something that is disjoint, whereas if we just use the ANs, then we know they're disjoint. So, it's the probability of A given E, which is equal to the probability of A intersection E divided by the probability of E. Now, I think what we'll do now is just replace A with all of these here. And I think that hopefully should just fall out nicely for us. And now I've lost where I am. So we're going to have to take a good look at what we've got. So we've got that P bar of A was equal to the probability of A intersection E divided by the probability of E. And this was also equal to the probability of A given E. Okay. So this is equal to, what are we going to say it's equal to? It's equal to the probability, now just stick in for A, it's the union, n is equal to 1 to infinity of ANs intersection E over the probability of E. Now just use the fact that intersection distributes over union, and we get probability of the union, n is equal to 1 to infinity ANs intersection E over the probability of E, which is equal to the sum, n is equal to 1 to infinity. Firstly, AN intersection E is just equal to AN, because AN was no bigger than the bit that was in E. This is we're taking the probability of all of these. These are all disjoint, so it's equal to the probability of ANs, and they're all divided by probability of E. Now, this is a finite number, so we can just slip it in. N is equal to 1 to infinity of the probability of AN. Oh! And in fact, it would be better to leave in AN intersection E so that you see it more directly, probability of E. So leave that in there, don't call that AN. And basically, this is now the conditional probability of AN intersection given E, which is equal to P bar of AN. So I hope you've been able to follow that argument. Basically, if you haven't followed that argument, what I will outline for you exactly what we were trying to do, and hopefully you can sit down and think about it for yourself, and you'll see hopefully what I was trying to do at least. What I was trying to do was, basically, I took my sample space. The whole point of what I've been doing in this video was I took a larger sample space with a set of events on it and a probability measure, and then I took an event in it, and I said, I'm going to now say that event has happened. And now I'm only interested in the outcomes in here, so I'm going to basically take this and make it into a new, smaller sample space, which is E, and I want to make it into a probability space. So I want to define a set of events, so that is take any events that happened in this sample space, intersect it with E, and just keep that new bit, the bit that intersected with E, and call that an element in this new probability space's set of events, and that new probability space's set of events is denoted F intersection sign E, which would be read F restricted to E. And then we had to define this new probability measure on it, P bar, and the way that I defined that is you take any set in here A, you take any event rather in here A, and P bar of A is going to be is equivalent to saying the probability of A given E, and that's defined to be the probability of A bar I'll say intersection E divided by the probability of E, where A bar is just any element of F such that A bar intersection E is equal to A. Now, of course, as I've shown you, you could just let A bar equal A, because I've shown you that F intersection E, F restricted to E, is a subset of F. So you could just put A in there rather than... basically, all the differences is basically that is a subset, that isn't an element in the events, but you could take a bigger one there and find something like that, but it doesn't affect the answer basically. And all I was doing in that final bit was showing that if you define that to be your probability measure, it does obey the axioms of being a probability measure. So that is the concept of conditional probability, reducing the size, making a smaller probability space from an old one. It's basically saying event E has happened. Now, what is the probability that event A happens? So basically you take an event A and you say, well, take only the bit that is in E, because only that can happen anymore, and what is the probability that that happens now? And the probability that that happens is the probability of A intersection E divided by the probability of E. And note basically that, this is really stupid, I should call that B because A meant something different here. Basically, if you have another event, B, and you're given that that E has happened, just take the probability of this bit here, the probability of E intersection B, and scale it basically, normalize it by dividing it by the probability that E happens. And that's the way you do conditional probability. In the final little minutes of this video, I'm going to show you something called Bayes' rule. Bayes' rule. Okay, I think that's got a comma there, an asterisk rather there. Okay, so we know that the probability of A given E is equal to the probability of A intersection E divided by the probability of E. And I want to just stress what I was doing here was different. I was saying A intersection E is E here. So A here means something different. A means any old event in your sigma algebra of subsets. It doesn't necessarily have to be an event that is completely contained within E. So the probability of A given E is equal to the probability of A intersection E divided by the probability of E. Now, that implies that the probability of A intersection E is equal to the probability of A given E divided by the probability of E. Times the probability of E, rather. Now, similarly, we could ask what is the probability of E given A. So basically, what we're saying is, if you have a sample space like this, you have two events, E and A. Then, in this case, we're saying E has happened. What is the probability, or that this intersection happens now? The probability of A given that E has happened. Whereas now we're saying A has happened. What's the probability of this in the whole new probability space, which is A? And again, that's going to be equal to the probability of A intersection E divided this time by the probability of A, which implies that this probability of A intersection E is equal to the probability of E given A times the probability of A. And basically we can now equate those two there and say that the probability of A given E is therefore equal to the probability of A divided by the probability of E times the probability of E given A. And that there is Bayes' rule, which is a very important result in conditional probability. And we'll leave it there for today.